Listen to that sound. That low rhythmic pulse you just heard was not generated in a studio. That is not a sound effect pulled from a science fiction film. That is not a synthesizer or a composer trying to make space feel dramatic. That is the actual electromagnetic signature of Pluto captured by NASA's New Horizons spacecraft as it screamed past at over 50,000 kilometers per hour and converted into audio frequencies your ears can process. Pluto is making noise. And for decades, for most of recorded scientific history, we told ourselves it was dead. We called it small, we called it frozen, we called it a mistake. We stripped it of its planetary status in a vote that made international headlines, threw it into the cosmic discard pile, and gave it a new category name that nobody asked for: dwarf planet. Scientists debated whether it had ever deserved to be called a planet at all. Textbooks quietly replaced its image with a footnote. Children mourned it at science fairs with hand-lettered signs that said, "Pluto is still a planet in my heart." The world moved on to more interesting things. To Mars, to Europa, to the gleaming, flashy targets of the inner solar system where missions could be completed in years rather than decades. But Pluto did not get the memo, because beneath a shell of nitrogen ice so thick and so ancient it predates the dinosaurs by more than 3 billion years, beneath a surface so brutally cold it would freeze your blood before you finished a single breath, beneath terrain so alien and so vast and so geologically complex that the first geologists to study the flyby images said things that are not typically said in peer-reviewed science. There is water, not frozen water, not trace amounts of ice crystals, not the kind of water that planetary scientists politely note may have existed in an earlier epoch. Liquid water, a global ocean, warm enough, deep enough, old enough, and sealed from the universe under a roof of ice 200 kilometers thick, in total darkness, at the absolute frontier of the solar system, 4 billion kilometers from the nearest star. And the question, the one that keeps the scientists up at night, the one that makes astrobiologists cancel their vacations and tear up their grant proposals and stare at their ceilings at 3 a.m. running the same calculations over and over, hoping the answer changes, is not whether the ocean exists. We know it exists. The question is what is living in it. Welcome to the most dangerous discovery at the edge of the solar system. Welcome to the world we abandoned. Welcome to the world that, in 4 billion years of patient silence, may have been building something in the dark. Welcome to Pluto. Before we get started, if you love exploring the depths of space as much as we do, take a second to like this video and subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Part 1. The lie we told for 75 years. To understand what Pluto actually is, not what the textbooks said, not what the popular imagination decided, not what the International Astronomical Union voted on. In 2006, you need to understand how we found it, and how our assumptions about what it was shaped, distorted, and ultimately blinded us to what it could be. It begins in Arizona, in a darkroom smelling of chemical developer, in the pre-dawn hours of the 18th of February 1930. Clyde Tombaugh was 24 years old. He was not a credentialed astronomer. He was a Kansas farm boy who had built his own telescopes from farm machinery parts and had sent his drawings of Jupiter and Mars to the Lowell Observatory in Flagstaff, Arizona, hoping for feedback. Instead, they gave him a job, not an intellectually glamorous job, a grinding, repetitive, eye-straining job, comparing photographic plates of the sky taken days apart, looking for anything that moved between the exposures. Planets move relative to background stars. Everything else does not. You look for the moving dot. He had been doing this for nearly a year. Thousands of plates, billions of star images, nothing. On the 18th of February 1930, he loaded 2 plates of the constellation Gemini into a device called a blink comparator, a machine that rapidly alternates between 2 images so the eye can detect movement. And in the field of Gemini, a dot moved. Tombaugh, by his own account, sat back in his chair and said, quietly, to himself, "That's it." The discovery was announced on the 13th of March 1930, the 75th anniversary of the birth of Percival Lowell, the founder of the observatory, who had spent years predicting a ninth planet based on supposed irregularities in the orbits of Uranus and Neptune. The planet had been found, apparently vindicating Lowell's calculations. The Lowell Observatory got to name it. They chose Pluto, the Roman god of the underworld, the god of what lies beneath, the god of the hidden. The name, it turns out, was more prophetic than anyone knew. Almost immediately, Pluto began disappointing its discoverers. It was small, smaller than expected. As telescopes improved and measurements refined, the mass estimates kept shrinking. By the 1970s, it was clear Pluto was too small to have caused the gravitational perturbations Lowell had predicted. The perturbations themselves were later explained as measurement errors. Pluto had been found, not because of Lowell's calculations, but because of sheer systematic luck. The relentless blink comparing of a 24-year-old Kansas farm boy. The planet predicted by Percival Lowell did not exist. Pluto was something else. Something smaller. Something stranger. Something we didn't have a category for in 1930, and wouldn't have a category for until 1992. When the first Kuiper Belt object was discovered, and astronomers began to understand that Pluto was not the solar system's oddball ninth planet, but the largest and most complex member of an entirely different class of worlds, the icy, rocky, chemically rich bodies of the outer solar system. But category errors are powerful things. Once we called Pluto a planet, we treated it like one. We expected it to behave like one. We measured it against the standard of the 8 classical planets and found it lacking. Too small, too cold, too far, too eccentric in its orbit, too tilted in its axis. Too everything that a proper planet shouldn't be. We had given it a name, and in doing so we had given it an identity. And when the identity didn't fit, we didn't question the identity. We questioned Pluto. This is the foundational error. This is the 75-year mistake, and it had consequences that extend beyond taxonomy, beyond the question of what to call a rock at the edge of the solar system. Because the classification determined the attention. Planetary status means missions. Planetary status means funding. Planetary status means the hundreds of scientists and engineers whose careers are devoted to exploring that world. When you call something a planet, people want to go there. When you call something a dwarf planet, they want to go somewhere else. Between 1930 and 2006, no spacecraft visited Pluto. Not one. Not a flyby. Not a probe. Not even a serious mission study that received funding. The Voyager missions, which revolutionized our understanding of Jupiter, Saturn, Uranus, and Neptune in the 1970s and 1980s, could have been redirected to include a Pluto flyby. The trajectory was possible. The opportunity existed. It was declined. Pluto was too small, too far, too unimportant. So we pointed our telescopes at Pluto from Earth's surface and made the best measurements we could from 4 to 7 billion kilometers away, depending on where each body was in its orbit. We established the basics. It had a moon, Charon, discovered in 1978. It had an atmosphere, discovered in 1988 when Pluto passed in front of a star, and the star's light was briefly dimmed and refracted. It had a surface of nitrogen ice and methane ice and carbon monoxide ice, the products of an unimaginably cold chemistry. It had a reddish coloration in places, suggesting organic chemistry on the surface. Interesting. Certainly worth noting. But not interesting enough, according to the institutional logic of planetary science funding, to justify a billion-dollar mission to a small, distant, probably geologically dead body at the edge of the solar system when there were more compelling targets in the inner solar system. And so the most consequential world in the outer solar system sat unvisited, its secrets sealed under ice, its ocean undiscovered, its geological activity unobserved, its status as an ocean world, one of the most scientifically significant categories of body in the solar system, entirely unknown and entirely unconsidered. For 75 years. The cost of that assumption is not measured in dollars. It is measured in decades of questions we could have been asking but weren't, in discoveries we could have made but didn't, in the possibility that somewhere in the archives of Pluto science there are data points that, if we had collected them in 1990 instead of 2015, would have already reshaped astrobiology, planetary science, and our understanding of where life can exist. The cost of deciding in advance what something is before you look is always the same. You miss what it actually is. Part 2. The Arrival. On the 19th of January 2006, at Cape Canaveral, Florida, a spacecraft the size of a baby grand piano was loaded onto an Atlas V rocket and launched into the Florida sky on the fastest trajectory ever achieved for a departing spacecraft. New Horizons left Earth at 58,536 kilometers per hour. It crossed the orbit of the Moon in 9 hours. It crossed the orbit of Mars in less than 3 months. It flew past Jupiter in February 2007, using the gas giant's gravity as a slingshot to boost its speed and shave years off the journey. It crossed the orbit of Saturn, the orbit of Uranus, the orbit of Neptune. It kept flying, its nuclear battery slowly fading, its radio signal growing weaker as the distance from Earth grew, 1 light minute, then 2, then 3, then 4. For 9.5 years, New Horizons flew. On the 14th of July 2015, it arrived. The lead-up to closest approach was a period of controlled anxiety unlike anything the planetary science community had experienced in decades. Images began flowing in weeks before the flyby first blurry, then sharper still, each improved resolution raising more questions than it answered. There were light patches and dark patches. There was something that looked like a bright region in the Western Hemisphere. There were hints of surface complexity that did not fit any model. Then the closest approach images arrived, at a data rate slower than a 1990s dial-up internet connection because the radio signal was travelling 4.5 hours at the speed of light from 3 billion miles away, the highest resolution. Photographs in planetary science history began downloading, frame by frame, into the computers at the Johns Hopkins Applied Physics Laboratory in Maryland. The first clear, high-resolution image showed a surface nobody had predicted, a surface nobody had even seriously imagined. Mountains. Towering peaks of water ice, not rock, water ice rising 3.5 kilometers above the surrounding plains. Sharp-edged. Geologically young. Free of impact craters, which in planetary science means free of the accumulated damage of billions of years of bombardment, which means the surface is new, being refreshed, recently formed. And to the west of the mountains, a vast, impossibly smooth plain of nitrogen ice, shaped. And this is not a metaphor. This is precisely what it looks like a heart. A bright, enormous, kidney-shaped expanse stretching more than 1,000 kilometers across. Smooth as glass. Actively convecting, with polygonal cells visible on the surface like the skin of a slowly boiling liquid. Young. Not millions of years old, not billions. Young in the geological sense, meaning it had been refreshed in the past tens of millions of years. On a world we said was dead. On a world that had been sitting in the cold and dark for 4.5 billion years. Alan Stern, the principal investigator of the New Horizons mission, the man who had spent 26 years fighting to build and fly this spacecraft, looked at these images and used words that do not typically appear in the vocabulary of planetary scientists at press conferences. He said, "I'm flabbergasted. I'm speechless. This is not the Pluto we expected." His team lead scientist Hal Weaver said, "This is the most complex terrain I have ever seen in our solar system." The geology team, looking at the mountain heights and the fresh surfaces and the absence of craters and the active convection of the nitrogen ice plains, started making the argument immediately. This geological activity required energy, heat, coming from somewhere inside Pluto, not from the Sun. The Sun's influence at 4 billion kilometers was too faint to drive this kind of surface renewal. From inside. And the only way to have internal heat on a small icy body in the outer solar system, 4 billion years after formation, is if you have a liquid layer that acts as a heat engine, a liquid layer that keeps the interior warm and mobile and geologically active. An ocean. Part 3. The evidence beneath the ice. The discovery of Pluto's ocean did not come as a single revelation. It came as a convergence, multiple independent lines of evidence, gathered from different instruments on New Horizons, pointing to the same conclusion with increasing certainty. The first line of evidence was the shape of Pluto itself. When New Horizons measured Pluto's gravity field in precise detail using the Doppler shift of the spacecraft's radio signal to infer the gravitational pull at different points along the trajectory, the data came back with an anomaly. The mass distribution of Pluto was not what you would expect from a uniformly solid frozen body. There was something wrong with the interior. The density variation suggested a differentiated structure, a rocky core, surrounded by a less dense layer, surrounded by the icy crust. This differentiation is normal for rocky planets. It is what happens when a body gets hot enough for heavier materials to sink and lighter ones to rise. But it suggests that Pluto was once hot enough on the inside to undergo this separation. And bodies that have been hot enough to differentiate, especially bodies being continuously kneaded by tidal forces from a large companion moon, often retain enough residual heat to maintain a liquid layer between the rocky core and the icy shell. The second line of evidence was the position of Tombau Regio. That heart-shaped plain of nitrogen ice is not just geologically young, it is in the wrong place. Not wrong in the sense that someone put it there incorrectly, wrong in the sense that the orbital dynamics and spin dynamics of Pluto predict it should be somewhere else. If Tombau Regio is a massive low-density surface feature sitting on top of a solid, uniform interior, Pluto's rotation should have gradually shifted so that Tombau Regio moved to a different latitude over geological time, a process called true polar wander, in which a massive surface feature migrates toward the equator because of rotational dynamics. Tombau Regio is not at the equator. It is in an unusual position relative to the tidal axis connecting Pluto to Charon. And the only way to explain why it stayed there, why true polar wander did not relocate it, is if there is something underneath it. Something massive and fluid. A subsurface ocean that redistributes mass as the surface feature forms, acting as a liquid counterweight that keeps the whole system balanced in its current configuration. The math works. The models have been run repeatedly by independent teams. The conclusion is the same. Tombau Regio is where it is because a subsurface ocean holds it there. The third line of evidence was the cracks. The surface of Pluto is covered in extensional fractures long, roughly parallel fissures in the crust running for hundreds of kilometers. Extensional fractures tell a story. They are the signature of a world that stretched, a world whose crust was pulled apart from below. When a liquid interior slowly freezes, when a subsurface ocean gradually crystallizes over billions of years, the volume change from liquid water to ice causes the overlying crust to stretch and crack. The pattern of Pluto's surface fractures matches, with remarkable precision, the pattern predicted by models of a freezing global ocean pushing outward against the crust. The orientation of the fractures, the density, the distribution, all consistent with a world whose interior expanded as a liquid layer crystallized. The fourth line of evidence was the heat. Not heat in the sense of warmth. You could feel Pluto's surface temperature as minus 230 degrees Celsius and would kill you in milliseconds. Heat in the geological sense. The excess thermal energy radiating from the interior that drives surface activity. The active convection of nitrogen ice in Tombau Regio requires heat from below. Something warm enough to drive the slow, viscous cycling of nitrogen ice from depth to surface and back. The young mountain terrain requires geological activity, driven by internal energy. The absence of impact craters on fresh terrain requires ongoing resurfacing. All of this requires an ongoing source of internal heat. Not ancient residual heat from billions of years ago that would have dissipated long since in a body as small as Pluto. Ongoing heat. Present tense heat. Heat being generated right now by a mechanism that is currently active. The most convincing mechanism supported by the most models, by the most teams, with the most consistency is a liquid water ocean kept warm by tidal heating from Charon and radiogenic decay in the rocky core. When you add these four lines of evidence together, the gravity anomaly, the position of Tombau Regio, the extensional fractures, and the present-day heat, flow the case for a current, active, liquid water ocean beneath Pluto's ice becomes not merely plausible, but very difficult to dismiss without a better alternative explanation. And no better alternative explanation has been proposed. The ocean is there. Part 4. The numbers that should stop you. Let me give you some numbers. Not to impress you with the scale of things, though the scale is genuinely staggering, but because without the numbers the human brain cannot process what we are actually talking about. Pluto's subsurface ocean is estimated to be approximately 100 to 180 kilometers deep. The deepest point in Earth's ocean is the Challenger Deep in the Mariana Trench, at 10.9 kilometers. Pluto's ocean is between 9 and 16 times deeper than the deepest point in our own ocean. If you place the entire height of Mount Everest above sea level 8.8 kilometers inside Pluto's ocean, it would disappear without reaching the surface. If you stacked 10 Everests on top of each other and dropped them in, they might just reach the waterline. The ocean has been liquid for approximately 4 billion years. To understand 4 billion years, consider this. The universe itself is only 13.8 billion years old. Pluto's ocean has been liquid for roughly 29% of the age of the entire universe. When the ocean formed, the Milky Way galaxy had already been spinning for nearly 10 billion years. Our solar system was brand new. Earth was a ball of molten rock being constantly hammered by impactors. There was no crust, no ocean, no atmosphere worth mentioning, no chemistry of life, not even the precursor molecules. And Pluto was already sitting at the edge of the forming solar system with liquid water. 4 billion years of continuous liquid water. On Earth, that timescale produced the following sequence. From the first simple single-celled organisms to every living thing that has ever existed on this planet, every bacterium, every alga, every jellyfish and trilobite and fern and dragonfly, and dinosaur and mammal and primate and human being, every civilization, every war, every artwork, every idea, everything that has ever lived and died and evolved on this planet did so in the time that Pluto's ocean has been liquid. 4 billion years is not a geological timescale, it is a biological one. It is exactly the timescale over which life on Earth went from chemistry to everything. Now think about what Pluto's ocean has been doing for those 4 billion years. Not moving, not evaporating, not draining away. Just sitting there, in the dark, under the ice, surrounded by chemistry, heated from below, sealed from the universe, running the slow, cold, patient chemistry of the deep. And we have been studying it, in any meaningful sense, for approximately 11 years. We have read one page of a 4 billion year book. Part 5, Charon and the Violence That Made the Ocean. No story about Pluto's ocean can be told honestly without telling the story of Charon, because Charon is not just a moon. Charon is the reason the ocean exists. Charon is the engine, the keeper, the gravitational partner that has been maintaining the temperature of an ocean it will never touch through billions of years of tidal embrace. In a gravitational relationship, so intimate and so precisely balanced that it is, in the vocabulary of orbital mechanics, genuinely extraordinary. Charon was discovered in 1978 by astronomer James Christie at the United States Naval Observatory. He noticed in some images of Pluto that the disk appeared slightly elongated, not circular as it should be, but bulging in one direction. The bulge turned out to be a moon, a large moon. Embarrassingly large for the body it orbited. Charon is approximately 1,214 kilometers in diameter. Pluto is approximately 2,377 kilometers in diameter. The ratio roughly 1/2 is unlike any other planet-moon relationship in the solar system. Earth's moon is about 1/4 the diameter of Earth. No other moon is more than roughly 1/3 the diameter of its parent body in any well-established planetary system. Charon is so large relative to Pluto that the center of mass of the Pluto-Charon system, called the barycenter, lies not inside Pluto but in empty space between the two bodies. They orbit each other. This is not the relationship between a planet and its moon. This is the relationship between two equal partners, bound by gravity, turning around a point in the space between them. Astronomers call it a binary system. The most precise term is double dwarf planet. There is nothing else quite like it in the solar system. And the tidal forces generated by this gravitational partnership are immense. When two large bodies orbit each other at close range, their gravity stretches and squeezes the interior of each body with every orbit. The interior of Pluto flexes. Rock and liquid and ice deform slightly in response to Charon's pull, and then spring back. This flexing generates heat. Not much heat by the standards of the inner solar system, where radiogenic decay in large rocky cores and solar insolation provide abundant thermal energy, but enough heat combined with the radiogenic decay in Pluto's own rocky core to keep a liquid water ocean from freezing at 4 billion kilometers from the Sunday. Without Charon, Pluto's interior would have cooled completely billions of years ago. The ocean would have frozen solid. the geological activity would have ceased. The nitrogen plains would not be convecting. The mountains would not be young. Pluto would be exactly the dead, featureless, cratered ice ball that planetary scientists expected before New Horizons arrived. Charon is the reason Pluto is alive. And Charon formed in violence. The leading model for Charon's origin is a giant impact. Early in the solar system's history, perhaps within the first 100 million years of planetary formation, another Kuiper belt body, a world perhaps half the size of Pluto, struck Pluto in an oblique collision of catastrophic force. The impact shattered both bodies. The impactor was destroyed entirely. Much of Pluto's outer layers were blasted off and flung into orbit. That orbital debris gradually coalesced, under gravity, into Charon. This is the same general process by which Earth's moon formed a giant impact early in the solar system, stripped material from the proto-Earth and assembled it into the moon. The parallel is not coincidental. Giant impacts were common in the chaotic early solar system when the orbits of the giant planets were still migrating and scattering material throughout the system. Both the Earth-Moon system and the Pluto-Charon system record the same violent chapter of solar system history. But the impact at Pluto had a consequence that the Earth-Moon impact did not. It created the conditions for a subsurface ocean at the absolute frontier of the solar system. The energy of the impact heated Pluto's interior. The tidal heating generated by the resulting large moon has sustained that heat for 4 billion years. The impact that should have been purely destructive turned out to be, in the most literal sense, generative. Violence created the conditions for life, or at least for the conditions that might support life. The universe does this repeatedly. The same impact that created the moon may have been critical for establishing Earth's axial tilt and seasonal climate stability conditions that may have been important for the evolution of complex life. The same process, scaled differently, operating at a different distance from the Sun in the cold outer solar system, may have established a liquid water world at Pluto. Two different outcomes of the same physical process, separated by 4 billion kilometers, both of them pointing toward the same possibility. The universe has one recipe, and it is not a gentle one. Part 6. The floor of the ocean. Let's go down. Not metaphorically, physically. Let's descend through the ice, through the ocean to the floor. To the place where, if anything is alive in Pluto's ocean, it almost certainly lives. You begin at the surface of Pluto. The temperature is minus 230 degrees Celsius. Nitrogen ice stretches in every direction, shaped by billions of years of sublimation and redeposition into formations that have no equivalent on Earth. You descend through the outer nitrogen ice layer, becoming colder as you go, a thought that seems impossible, because you are already colder than anything on Earth. But the temperature continues to drop until you reach the level where nitrogen ice gives way to methane ice, and then to carbon monoxide ice, and then, deeper, to a transition zone where the pressure and temperature begin to change. You pass through layers of increasingly pure water ice. The pressure increases with every kilometre. At 50 kilometres below the surface, the pressure is already several hundred times atmospheric. At 100 kilometres, you are approaching the pressures found at the bottom of Earth's deepest ocean trenches. At 150 kilometres, you reach the base of the ice shell, and then you break through into the ocean. The darkness is absolute. There is no bioluminescence here, or if there is, we have no way of knowing. There is no light from above, no sunlight filtering through even the most transparent ice at this depth. The water, if it behaves like water at these pressures and temperatures, which is a complex question involving the physics of high-pressure ice phases, is cold, slightly above the freezing point. Salty, based on geochemical models that predict dissolved minerals from the rocky core, chemically complex. You descend through the ocean, 100 kilometers down. It takes time. The water around you is not still. Current models suggest weak convective circulation driven by the temperature gradient between the cold ice roof above and the warmer rocky floor below. Dissolved gases rise. Denser water sinks. Slow, quiet, patient. And then you reach the floor. Not a smooth floor. Not a clean boundary between water and rock. A complex, irregular terrain of fractured silicate rock, the outer surface of Pluto's rocky core covered in the products of billions of years of water-rock interaction. Minerals dissolved and redeposited. iron compounds staining the rock in colours you cannot see because there is no light to see them by. And from fissures in the rock, warmed by the radiogenic decay of uranium and thorium and potassium deep in the core below, hydrothermal fluids. Water heated in contact with rock, minerals dissolved in the hot water, emerging from the rock surface and mixing with the cold ocean above, creating temperature gradients. Chemical gradients. The same architecture simplified, slower, colder, as the hydrothermal vent systems on Earth's ocean floor, where entire ecosystems thrive in complete darkness. At Earth's hydrothermal vents, the chemistry produces hydrogen through serpentinization, the reaction between liquid water and iron-bearing silicate rocks. The hydrogen diffuses into the surrounding water. Microbes, methanogens, hydrogenotrophic bacteria, sulfur-reducing archaea consume the hydrogen and use the chemical energy to drive their metabolisms. They produce methane. They produce sulfide. They build complex biochemistry from simple chemistry through the patient work of catalysis. At Pluto's ocean floor, the serpentinization chemistry almost certainly happens. The rocks are silicate, the water is liquid, the pressure and temperature are in the range where the reaction proceeds. Hydrogen is produced. The ocean floor of Pluto is, in all likelihood, a source of chemical energy. Now here is the precise question. The question that requires no speculation, only measurement. When hydrogen is produced at the floor of Pluto's ocean and diffuses upward into the water column, is anything consuming it? On Earth, the answer in a hydrothermal vent environment is always yes. Within what appears to be geological time, perhaps a few million years, life colonizes every available energy source. Life on Earth has been found consuming hydrogen in deep subsurface environments entirely disconnected from the surface biosphere. Life has been found in 100-million-year-old water pockets in deep mines, isolated from the rest of the biosphere for geological ages, surviving on hydrogen produced by water-rock interaction. Life is extraordinarily persistent. Life is extraordinarily resourceful. Does that apply on Pluto? We don't know. We haven't measured. We have not dropped a probe into that ocean. We have not analysed the water chemistry. We have not looked. The question of whether life consumes the hydrogen at the floor of Pluto's ocean is, as of right now, literally unanswered and literally answerable. It is not a philosophical question. It is a chemistry question. And it can be answered with the right instruments on the right mission. Part 7. The chemistry of the surface and what it tells us. Pluto's surface is a laboratory, not a clean, sterile, controlled laboratory. A 4-billion-year-old open-air chemistry experiment conducted by the combined forces of ultraviolet radiation, cosmic ray bombardment, sublimation cycling, atmospheric photochemistry, and the slow geological reshaping of a world in dialogue with its own interior. The products of that experiment cover Pluto's surface in a thin layer of dark reddish organic molecules called tholins. Tholins are not a single compound. They are a class of complex organic molecules produced when simple carbon-containing gases, methane, nitrogen, carbon monoxide, are exposed to radiation. The radiation breaks the simple molecules apart, and the fragments recombine into longer, more complex chains. Given enough time and enough radiation, the complexity increases. The chains grow longer. The molecules become more varied. The chemistry begins to approach, not reach, but approach the chemical complexity of the prebiotic soup that existed on early Earth before life began. Tholins are found throughout the outer solar system, on Titan, on the surface of comets, on the dark regions of Charon's poles, and extensively on Pluto, colouring much of its surface in shades of brown and red and orange that stand out against the brighter nitrogen and methane ice. The tholins are not alive, let's be absolutely clear about that. They are complex organic molecules produced by radiation chemistry, and organic molecules are not life any more than the individual letters of the alphabet are a novel. But they are the kind of chemistry that, on a warmer, wetter world, becomes the building blocks of life. The amino acids, the 20 molecules from which all proteins on Earth are assembled, can be produced abiotically in tholins chemistry under the right conditions. Laboratory experiments have produced amino acids from mixtures of methane and nitrogen and water exposed to radiation conditions that approximate the surface chemistry of icy outer solar system bodies. Now think about the pathway from surface to ocean. At the time of Pluto's formation and in the period following the giant impact that created Charon, Pluto's interior was dramatically hotter than it is today. The heat of formation, the heat of accretion, the heat of the giant impact itself, all of this raised the interior temperature enormously. The ice shell was thinner, the ocean was closer to the surface, perhaps much closer. In that early period, the connection between surface and ocean was more direct. Cracks would have extended all the way from the surface to the ocean. Impact events would have punched through the thin ice, delivering surface material including tholins, including organic chemistry accumulated in the first few 100 million years directly into the ocean below. Those molecules have been in the ocean ever since. And in 4 billion years of sitting in warm, chemically active water adjacent to a hydrothermally active rocky floor, those organic molecules have had the opportunity to do something that organic molecules in liquid water in contact with heat sources do. They interact, they react, they form more complex structures. They explore the chemical space of possible molecular configurations in ways that, given enough time and enough energy, occasionally stumble upon self-replicating structures. We do not know if that stumbling happened. We do not know if the chemistry of Pluto's ocean crossed the threshold from complex chemistry to chemistry with agency, chemistry that copies itself, chemistry that evolves, chemistry that we would recognize as life. But the pathway exists. The chemistry is there. The energy is there. The time is there. The experiment has been running for 4 billion years. Part 8. The methane signal. There is a measurement that a future mission to Pluto could make that would, if it returned the right result, be the most consequential scientific measurement in the history of our species. It involves methane. Pluto's thin atmosphere, discovered in 1988 and confirmed in detail by New Horizons, contains methane. This is expected. Methane ice covers significant portions of Pluto's surface, and at Pluto's surface temperature, a small amount of methane is always in the vapor phase, contributing to the tenuous atmospheric envelope. The atmospheric methane signal is well established. It is one of the most robustly measured features of Pluto's atmosphere. But methane has a property that makes it scientifically extraordinary in the context of astrobiology. It is a biosignature. Not automatically, not always, but potentially, because the methane produced by geological processes and the methane produced by biological processes have measurably different isotopic compositions. Carbon exists as several isotopes: carbon 1,2, the most abundant, and carbon 1,3, a slightly heavier version. When methanogens, the microbes that produce methane as a metabolic byproduct, synthesize methane from hydrogen and carbon dioxide, they preferentially incorporate the lighter carbon, 1,2, into the methane molecule and leave the heavier carbon, 1,3, behind. The result is methane with a lower ratio of carbon, 1,3 to carbon, 1,2, than the source material. This preference for lighter isotopes is a feature of enzymatic reactions, the biological machinery of metabolism, and it is consistent enough that it serves as a diagnostic tool in earth science. When geologists want to determine whether methane in a sample is biogenic or abiogenic in origin, they measure the carbon isotope ratio. The atmospheric methane at Pluto currently cannot be distinguished, with the instruments we used during the New Horizons flyby, as biogenic or abiogenic. The flyby instruments were not designed for isotopic analysis. The data rate was too slow, the encounter too brief, the payload too constrained. But a dedicated orbiter with a high-resolution mass spectrometer, an instrument that can measure the precise ratio of carbon, 1,2 to carbon 13 inches individual molecules, could make this measurement. It has been done from orbit before. The Mars Science Laboratory and Mars Express missions have both made similar atmospheric composition measurements at Mars. The technology is well established. If a future Pluto orbiter measured the atmospheric methane and found that the carbon isotope ratio was consistent with biological fractionation, if the methane at Pluto was isotopically light in the way that biogenic methane is, isotopically light, the interpretation would be inescapable. Something alive in Pluto's ocean is producing methane. That methane is making its way from the ocean to the atmosphere through geological connections between the subsurface and the surface. And life on Pluto has been exhaling into the atmosphere of the solar system's most remote world for at least as long as the geological record of Pluto's surface preserves evidence of the current atmospheric chemistry. This measurement is possible. The instrument exists. The mission concept exists. The science case is unambiguous. The decision to build and launch the mission has not yet been made. Part 9. The world that mirrors Earth and exceeds it. There is a philosophical confrontation at the heart of the Pluto story that scientists tend to avoid in public communication because it sounds too dramatic, too science fictional, too much like the kind of claim that gets distorted in headlines and comes back to embarrass the scientist who made it. But it deserves to be stated plainly. Pluto's ocean, if it harbours life, is not similar to Earth's ocean. It is not an environment that life on Earth could survive in. The temperature is just above 0 degrees Celsius. The pressure at depth is extreme. There is no light. The energy flux is orders of magnitude lower than in Earth's sunlit ocean surface waters. The chemistry is different, more hydrogen-rich, less oxygen-rich, with different dissolved minerals and different pH characteristics. And yet, in a specific and important sense, the conditions in Pluto's subsurface ocean more closely resemble the conditions in which Earth's deepest and most ancient life evolved than the conditions on Earth's surface today. The hydrothermal vent systems at the bottom of Earth's ocean, particularly the alkaline hydrothermal vent systems like the Lost City hydrothermal field in the Atlantic Ocean, are considered by many origin of life researchers to be the most likely birthplace of life on Earth. Not the sunlit surface, not the warm little pond that Darwin imagined. The cold, dark, chemically energetic interface between liquid water and hot rock, where hydrogen and carbon dioxide react in the presence of mineral catalysts to produce the organic molecules that eventually, through a process still debated but increasingly well understood, began to self-replicate. The Lost City vents produce hydrogen. They produce methane. They produce organic molecules of increasing complexity. The chemistry there is, in the language of biochemistry, prebiotic, before biology, producing the molecules from which biology can emerge. Now compare that to the floor of Pluto's ocean. Cold liquid water in contact with a hydrothermally active rocky core, producing hydrogen through serpentinization, producing methane as a chemical byproduct, accumulating organic molecules that have been delivered from the surface over 4 billion years of geological history. The conditions are not identical, but they are not dissimilar. And the conditions at the Lost City vents on Earth are the conditions that many origin of life researchers consider the most favourable on Earth for the origin of life. If life began at conditions similar to those at the Lost City vents, and if conditions similar to those at the Lost City vents exist at the floor of Pluto's ocean, then the floor of Pluto's ocean is not an unlikely place for life to have emerged. It is, by the logic of origin of life research, one of the more likely ones. And there is something more. The Lost City hydrothermal field on Earth was discovered in 2000. Before its discovery, hydrothermal origin of life theories focused primarily on the high-temperature black smoke events discovered in the 1970s. The discovery of the Lost City cooler, more chemically gentle, more chemically complex, more hospitable to the specific reactions that origin of life chemistry requires, fundamentally changed the scientific landscape of theories about how life began. The Lost City has been operating on Earth for approximately 30,000 years. It is geologically young. The hydrothermal activity at the floor of Pluto's ocean has been operating for 4 billion years. The conditions that produced life on Earth operated for tens of thousands of years before life appeared. Pluto's equivalent conditions have been operating for 4 billion years, 100,000 times longer. If there is a threshold of time below which life does not emerge, even given the right conditions, and the chemistry of Earth's origin of life suggests there might be, Pluto's ocean has almost certainly passed it. Part 10. The scientists who refuse to stop looking. Science is a human enterprise. It is conducted by people who have limited time, limited funding, institutional allegiances, career pressures, and the universal human tendency to believe that what they already know is probably mostly right. The story of Pluto's ocean is also, therefore, a human story. A story about a small group of scientists who looked at the same data everyone else, looked at the preliminary New Horizons results, the models of Pluto's interior, the atmospheric measurements, the geological maps, and drew conclusions that most of their colleagues considered premature at best and probably overclaimed. Among them is Francis Nimmo at the University of California, Santa Cruz, whose work on the interior dynamics of icy worlds, particularly his modelling of the conditions required to maintain a subsurface liquid ocean on Pluto, produced some of the earliest and most quantitative arguments for Pluto's ocean being current rather than ancient. Nimmo's models are careful and hedged, as good scientific models are. They present ranges of outcomes based on ranges of assumed parameters. But the central tendency of his results, the most likely outcome, consistently pointed toward a present-day liquid ocean. Among them is Kelsey Singer at the Southwest Research Institute, the same institution that built and operates New Horizons, whose analysis of Pluto's impact crater record provided a window into the geological history of the free surface. By counting and sizing and analysing the distribution of craters, Singer and her colleagues reconstructed the bombardment history of the Kuiper Belt and used it to constrain the ages of Pluto's different terrain units. The conclusion: some of Pluto's surfaces are extraordinarily young. Some are nearly devoid of craters at all, meaning they have been resurfaced so recently that the statistical bombardment rate predicts essentially no craters should yet have accumulated. Young surfaces mean ongoing geological activity. Ongoing geological activity means ongoing internal heat. Ongoing internal heat means a current liquid interior. Among them is Linny Quick at NASA's Goddard Space Flight Center, who has spent her career studying ocean worlds, not just Pluto, but Europa and Enceladus, and the broader class of icy bodies with subsurface liquid. Quick's work draws connections between these different worlds, finding the common physical principles that explain how tidal heating and radiogenic decay can maintain liquid water over geological timescales at enormous distances from the sunday. Her work places Pluto firmly within the class of ocean worlds, not an outlier, not a special case, but a member of a category of bodies that the solar system contains in abundance. And among them is Alan Stern himself, who is not primarily an ocean world scientist, but who built the mission that found the ocean. Stern's argument for New Horizons was never Pluto might have liquid water. That would have been too bold a claim in the 1990s and early 2000s when he was fighting to get the mission funded. His argument was simpler and harder to dismiss. We have never been to the most distant region of the solar system, and we should go. Whatever we find will be important. Whatever we find will teach us something we do not know. The history of solar system exploration shows that every body we visit in detail surprises us. Pluto will surprise us. He was correct. But even he, who had staked 26 years of his professional life on the argument that Pluto was worth visiting, who had built the spacecraft and assembled the team, and withstood the funding cuts and the cancellations and the institutional resistance, even he was not fully prepared for what the flyby images showed. Because Pluto did not just surprise them, Pluto broke their models. Part 11. The Kuiper Belt and the Primordial Ocean. Pluto does not live alone. It is the largest member of a vast population of bodies occupying the outer solar system, a region called the Kuiper Belt, extending from roughly 30 to 50 astronomical units from the Sun, containing hundreds of thousands of icy, rocky, chemically complex bodies ranging in size from small fragments to objects nearly as large as Pluto itself. The Kuiper Belt is not a junkyard, it is an archive. The bodies in the Kuiper Belt are the remnants of the solar system's formation material that was not incorporated into the giant planets during the first few million years of planetary assembly, and which has been sitting in the cold outer solar system ever since, largely unchanged by the geological and chemical processes that have dramatically altered the inner solar system over 4.5 billion years. When New Horizons flew past the Kuiper Belt object Arakoth in January 2019, it returned images of something truly primordial. Arakoth is a contact binary two lobes of an icy body that gently came together in the early solar system and merged without violence, preserving the structure of the original building blocks of planets. Its surface is covered in tholins. It is red, it is complex in its chemistry, and it has been sitting unchanged, in the cold and dark, since before the planets of the inner solar system had finished forming. Arakoth is a message from the beginning, an artifact of creation, a sample of the raw material from which everything, Earth, Mars, Jupiter, and every planet in every other solar system was assembled, and it is made of the same chemistry as Pluto's surface. Now consider what this means for the question of life's origin. The current leading model of how life's building blocks arrived on early Earth involves delivery from space. Comets and carbonaceous asteroids' bodies made partly of the same icy organic-rich material as Kuiper belt objects impacted early Earth during the late heavy bombardment approximately 4 billion years ago, delivering water, amino acids, nuclear bases, and other organic molecules that may have contributed to the prebiotic chemistry from which life eventually emerged. This is called the panspermia adjacent hypothesis of molecular delivery. Not the idea that life itself came from space, but the idea that the raw materials of life were partly extraterrestrial in origin. The Kuiper belt was the source of many of those delivery vehicles. The comets that bombarded early Earth were, in many cases, Kuiper belt objects perturbed into the inner solar system by the gravitational influence of Jupiter and Saturn. The chemistry they carried, the tholins, the organic molecules, the water and carbon and nitrogen compounds, was the chemistry of the outer solar system. The same chemistry now sitting on Pluto's surface. Pluto is therefore not alien to the story of life on Earth. Pluto is part of it. The molecules on Pluto's surface are cousins to the molecules that seeded the chemistry of early Earth. The icy material from which Pluto was assembled is related to the material from which the comets were assembled that delivered organics to our planet. The chemical record preserved in Pluto's ancient radiation processed surface is a record of the raw materials of life in the solar system. To go to Pluto is not to go somewhere foreign, it is to go to the source library, the place where the original chemical texts are stored before they were edited by 4.5 billion years of geological processing on the inner planets. You are, in a measurable chemical sense, made partly of material that once resembled Pluto. This is not poetry, this is isotope geochemistry. Part 12. The ice shell as a world unto itself. Before we descend to the ocean, we need to stop in the ice, because the ice is not a barrier. It is not simply an obstacle between us and the water below. The ice shell of Pluto is itself an environment of extraordinary complexity, one that has barely received the scientific attention it deserves because the ocean beneath it is so much more dramatic. The ice shell begins at the surface with nitrogen, pure, crystalline, brutally cold nitrogen ice, the substance that covers the floor of Tombaugh Regio and gives it its blinding brightness. Nitrogen ice at Pluto's temperature is a peculiar material, softer than water ice, more mobile, prone to flowing under the influence of gravity and pressure differentials in the way that glacier ice flows on Earth, but on timescales of millions of years rather than thousands. The convection cells visible on the surface of Tombaugh Regio, the polygonal patterns that resemble the surface of a cooling soup or the skin of a slow-boiling fluid, are the surface expression of this flowing nitrogen. Ice, cycling from depths of several kilometers to the surface, and back in a slow, patient rotation driven by the heat from below. Beneath the nitrogen ice layer, the temperature and pressure increase. The nitrogen gives way to methane ice. The methane ice is different in character, harder, more resistant to flow, photochemically active in ways that produce tholins from the interaction of radiation with the methane molecules. The reddish coloration of many of Pluto's surface regions is the accumulated product of this photochemistry. Billions of years of radiation breaking methane molecules into fragments that recombine into increasingly complex organic structures. Deeper still, the methane gives way to water ice, pure ancient water ice, compressed by the weight of hundreds of kilometers of material above it. Water ice under pressure behaves differently from the water ice in your freezer. At the pressures found deep in Pluto's ice shell, water ice can exist in several different crystalline phases, high-pressure ice structures with different densities and different thermal properties from ordinary surface ice. The transition between these phases releases or absorbs heat, adding complexity to the thermal structure of the ice shell. And at the very base of the ice shell, at the interface between the solid ice above and the liquid ocean below, there is a zone that may be, in the vocabulary of astrobiology, among the most interesting regions in the entire solar system. This interface where liquid water meets the underside of the solid ice is a transition zone. Temperature gradients are steepest here. Chemical exchange between the ocean and the overlying ice is most active here. Dissolved minerals from the ocean are being continuously incorporated into new ice at the base of the shell, and material at the ice-ocean boundary is being constantly recycled as the ocean convects from below. The boundary is dynamic, it is chemically active, and it extends across the entire base of the global ice shell, a surface area of approximately 12 to 16 million square kilometers, as we established, larger than the entire continent of Africa. On Earth, biological life concentrates at interfaces: the surface of the ocean, the shoreline between sea and land, the chemocline where oxygenated water meets anoxic water in stratified ocean basins, the sediment-water interface at the ocean floor. Everywhere that different chemical environments meet, life finds a way to exploit the energy gradient between them. The steeper the gradient, the higher the biological productivity. The ice-ocean interface at Pluto is in principle an interface, a steep gradient between cold, solid ice above and slightly warmer, chemically richer liquid ocean below. If life exists in Pluto's ocean and has had 4 billion years to explore its chemical environment and optimize its metabolic strategies, it is not unreasonable to imagine that it has discovered the ice-ocean interface as a chemical resource, as a surface where minerals concentrating at the base of the ice provide resources not available in the open water. Column. We do not know if this happens, but the physics and chemistry do not forbid it. And on Earth, the equivalent environments, the ice-water interface beneath the Antarctic ice sheet in subglacial lakes, the sea-ice-ocean interface in polar regions are indeed biologically active, in ways that surprised the scientists who first studied them. The ice itself may not be lifeless. Part 12b, the atmosphere as a window. Pluto's atmosphere is thin, extraordinarily thin. At the surface, the atmospheric pressure is approximately 10 to 25 microbars, 10 to 25 millionths of Earth's surface pressure. A pressure so low that you could not survive in it for a fraction of a second even if the temperature were not lethal. A pressure so low that breathing it would be meaningless. There is no meaningful mass of gas to inhale. And yet this atmosphere is scientifically precious in ways that a thicker atmosphere on a closer world might not be. Precisely because it is thin, precisely because it contains such small quantities of gas, any chemical signal in it is proportionally more significant. Any anomaly in its composition is harder to explain away. Pluto's atmosphere has been analysed in detail by New Horizons. It contains nitrogen, the dominant component, sublimated from the nitrogen ice surface. It contains methane, sublimated from the methane ice, and produced by photochemistry. It contains carbon monoxide, and it contains complex organic molecules in the higher atmospheric layers, where haze particles made of tholins create the delicate blue coloration that stunned the New Horizons team when the first backlighted images of Pluto came back from the flyby. That blue haze. It deserves a moment of dedicated attention because it is both scientifically informative and, in the most straightforward aesthetic sense, beautiful. When the Sun is behind Pluto, when New Horizons looked back toward the inner solar system after closest approach and captured Pluto as a silhouette against the darkness of space, the edge of the planet glowed with a thin blue ring of scattered light, concentric rings of haze at different altitudes, each layer produced by a different altitude of photochemistry, each slightly different in its particle size distribution and optical properties. This is not a passive, static atmosphere. It is active. It is chemically processing material continuously. Methane and nitrogen and carbon monoxide are being broken apart by ultraviolet radiation and cosmic rays and reassembled into organic molecules of increasing complexity. Some of those molecules precipitate back to the surface, building up the tholin deposits. Others remain in the gas phase. Others are lost to space. Pluto's gravity is weak enough that energetic atmospheric molecules can escape to space entirely, in a process called atmospheric escape, contributing to a thin cloud of material that follows Pluto in its orbit. The atmospheric chemistry is a factory. It takes simple molecules and builds complex ones. And those complex molecules, the tholins, the larger organic species, are the same class of chemistry that, on early Earth, constituted the prebiotic molecular inventory from which life assembled itself. If you could collect a sample of Pluto's atmospheric tholins and run them through a mass spectrometer, you would find amino acids. Not necessarily the 20 amino acids used by Earth life. Not necessarily the specific configurations that Earth's biochemistry employs. But amino acids, the fundamental class of molecules from which proteins are built, the fundamental chemical architecture of life's machinery, the same raw material, the same category of compound. The atmosphere of Pluto is exhaling the building blocks of life into the solar system. Not intentionally, not biologically, chemically, through the patient, slow, radiation-driven synthesis of complex organic molecules from simple ones in the cold outer atmosphere of a world at the edge of everything. But the molecules are there, and they fall back to the surface. And they have been doing this for 4 billion years, and some fraction of what falls to the surface finds its way, through geological processes, into the ocean below. The atmosphere is not separate from the ocean story. The atmosphere is part of it. It is the chemical input line, the supplier, the slow, continuous drip of organic complexity from sky to surface to, eventually, ocean. Part 12c. Time, evolution, and what 4 billion years actually produces. We have used the phrase 4 billion years many times in this documentary. We have compared it to the age of life on Earth, to the age of the solar system, to the fraction of the universe's age it represents. We have tried to make the number real through comparisons and context. But there is one comparison we have not yet made, and it is perhaps the most important one. Life on Earth has been evolving continuously for approximately 3.8 billion years. In that time, it has gone from the simplest possible self-replicating chemistry to the full diversity of the biosphere. 5 kingdoms of life, estimated at anywhere from 8 million to 1 trillion distinct species, occupying every environment, from the bottom of the Mariana Trench to the top of the stratosphere, from the interior of nuclear reactors to the permafrost of Siberia, from the acidic hot springs of Yellowstone to the hypersaline depths of the Dead Sea. But here is the critical asymmetry. The vast majority of that evolution, the vast majority of the diversity of life on Earth is microbial. The complex multicellular life we tend to think of when we say life, animals, plants, fungi, has existed for only about 600 million years. 600 million years out of 3.8 billion. That is approximately 16% of the total history of life on Earth. For the other 84% of life's history, for the first 3.2 billion years, life was entirely microbial. Single cells, archaea, bacteria, communities of microbes building stromatolites and processing the chemistry of the atmosphere and ocean and rock without any multicellular organization at all. Those 3.2 billion years of microbial evolution produced extraordinary things. Photosynthesis, the invention of using sunlight to drive chemistry, was a microbial innovation that transformed Earth's atmosphere and eventually made complex life possible. The endosymbiosis that produced the eukaryotic cell, the cell with a nucleus and membrane-bound organelles that constitutes the basic unit of all complex life, was a microbial event, one single-celled organism engulfing another and co-opting its chemistry. The nitrogen cycle, the sulfur cycle, the carbon cycle, the fundamental chemical loops that keep Earth's chemistry in balance and that make the planet habitable, are products of microbial metabolism evolved over billions of years. Microbial evolution is not simple or slow or uninteresting. It is the most productive, most chemically innovative, most evolutionarily prolific form of biology the universe has yet produced. It is the foundation on which everything else was built. Now apply that to Pluto. If life arose in Pluto's ocean at approximately the time life arose on Earth 4 billion years ago, give or take a few 100 million years, then Pluto's life has been evolving for the same duration that Earth's life has been evolving. In the same energy-limited, chemically constrained environment, yes. In a different chemical milieu, yes. But for the same length of time. The microbial life in Pluto's ocean, if it exists, has had 4 billion years to explore chemical space, to develop novel metabolic strategies, to build biochemical machinery of extraordinary sophistication for doing exactly one thing with maximum efficiency, extracting energy from the chemistry of hydrogen and rock and water in the complete dark under immense pressure. We do not know what 4 billion years of evolution in that specific environment produces. We have no model. Earth's deep biosphere gives us a hint the microbes living in deep rock on Earth are metabolically streamlined to a degree that surface life is not, their genomes pared down to the minimum necessary for survival, their metabolic rates so slow they are barely distinguishable from chemistry. But Earth's deep biosphere has only been isolated from the surface biosphere for tens to hundreds of millions of years, not 4 billion. And Earth's deep biosphere began with complex life that was then simplified by the constraints of the environment. Pluto's life, if it exists, began in those constraints and has never known anything else. The evolutionary trajectory of life that has never seen light, never experienced seasons, never interacted with any environment outside a sealed dark ocean under ice, for 4 billion years, is entirely outside our experience. We have no reference point. We have no model. We have no prediction. We only know that 4 billion years is enough time to produce, on Earth, everything that has ever lived. What it produced at Pluto is a question only the ocean can answer. Part 12. D. The technology that could listen. The instruments needed to detect life in Pluto's ocean, or to definitively establish its absence, are not hypothetical. They exist. They have been built, tested, and flown on previous missions. The challenge is not technological invention. It is engineering integration and the sustained political and financial will to build and launch the mission. A Pluto orbiter's primary astrobiological tool would be an atmospheric mass spectrometer capable of isotopic analysis. On Earth, isotope ratio mass spectrometers are used routinely in geology, ecology, archaeology, and environmental science. The space-qualified versions of these instruments have flown on the Cassini mission to Saturn and Titan, on the Mars Science Laboratory, and on the European Space Agency's Rosetta mission to Comet 67P. They are mature, well-characterized instruments. The challenge of deploying one at Pluto is the communication delay and the power budget, both manageable with existing technology. The second key instrument is an ice-penetrating radar. This technology, called ground-penetrating radar in Earth applications and subsurface radar sounding in planetary contexts, works by transmitting radio waves that penetrate through ice and measuring the reflection from density boundaries beneath. It is currently flying on the Europa Clipper mission, which launched in October 2024. The same instrument, appropriately scaled and powered, could map the structure of Pluto's ice shell, measure its thickness, identify the ice-ocean interface, and characterize the geometry of any features at the boundary between the solid ice and the liquid ocean below. The third instrument category is a thermal mapper, an infrared instrument that measures heat flow from the surface, constraining the rate at which internal heat is escaping from Pluto's interior. This directly measures the energy budget of the interior, constraining whether the interior is warm enough to maintain a liquid ocean. Thermal mapping from orbit has been done at Mars, the Moon, and other solar system bodies. It is not exotic. The fourth is a magnetometer. Pluto almost certainly does not have a strong global magnetic field. It is too small and too slowly rotating to generate one. But a liquid water ocean with dissolved salts is electrically conducting, and an electrically conducting layer inside a rotating body moving through the solar wind's magnetic field generates an induced magnetic field that a sensitive magnetometer can detect from orbit. This is the technique used by the Galileo mission to confirm the subsurface oceans of Europa and Ganymede. The same physics applies at Pluto. A magnetometer sensitive enough to detect the induced field from Pluto's ocean would provide direct confirmation of a conducting liquid layer. In other words, direct confirmation of a saline ocean without requiring any penetration of the ice. These four instruments, mass spectrometer, radar sounder, thermal mapper, magnetometer, flying together on a Pluto orbiter, would within the first few years of the orbital mission directly image the ocean through the ice, confirm its geometry and depth, measure the thermal energy budget of the interior, characterize the ocean's salinity and electrical conductivity, and analyze the atmospheric chemistry with precision sufficient to distinguish biological from abiological methane. This is the mission. This is the science it would do. These are the instruments. This is what we can accomplish. What it requires is the launch. Part 12e. The weight of the question. There is a moment in the career of every planetary scientist who works on ocean worlds, every researcher who spends their professional life thinking about the conditions for life beyond Earth when the weight of what they are doing becomes temporarily too large to hold inside the clinical framework of scientific language. It is the moment when the peer-reviewed hedging and the careful, consistent with, and the appropriately cautious does not rule out, all fall away, and what remains is the bare, unmediated fact. Somewhere in the outer solar system, there may be something alive that has never heard a sound, never seen a photon of light, never experienced a season or a current or any perturbation of its environment beyond the slow, dark, constant chemistry of rock and water. Something that has been alive, in its way, since before the first animal drew its first breath on Earth. Something that does not know we are looking. Something that does not know we exist. The weight of that possibility is not purely scientific, it is philosophical. It is deeply personal in a way that most scientific questions are not. The question of whether life exists elsewhere in Pluto's ocean, in Europa's ocean, on a moon of a distant gas giant in another galaxy, is not merely a question about chemistry or biology or planetary physics. It is a question about meaning, about significance, about whether the 4 billion years of evolution that produced us, the billions of years of stellar history that produced the carbon and oxygen and nitrogen of which we are made, the 13.8 billion years of cosmic history that produced the conditions for stars and planets and chemistry to exist at all, whether all of that is a story about just one place, or about something more. If Pluto's ocean is alive, even with the simplest single-celled organisms, the answer is unambiguous. Life is not the story of Earth, it is the story of the universe. It is what the universe does. Everywhere the conditions are met, everywhere the chemistry is right, everywhere the water is liquid and the energy is available and the time is sufficient, the universe is not a place where life happened. The universe is a place where life happens. And if that is true, then every lonely night you have ever spent looking up at the stars and feeling small, every moment when the scale of the cosmos made your own existence feel insignificant, contains its own implicit answer. You are not small because the universe is large and empty. You are small because the universe is large and full. You are one expression of a process that the universe runs everywhere it can. Not unique, not a cosmic accident, part of something far larger than accident. That is the weight of the question. That is what a microbe in the dark beneath Pluto's ice, silently metabolizing hydrogen in an ocean that has been there since before your planet had a crust. That is what it would mean if it were there. The mission matters, not just to science, to the story we tell about what we are and where we came from, and whether we are alone. That story deserves its answer. Here is a number that takes a moment to fully arrive. If Pluto's ocean has the surface area of a sphere with a radius of approximately 1,150 kilometers, which is approximately the outer radius of Pluto's rocky core, plus the depth of the ocean, then the total surface area of Pluto's ocean floor is approximately 16.6 million square kilometers. The total surface area of Africa is approximately 30.4 million square kilometers. Pluto's ocean floor has a surface area of more than half the African continent. Now scale that image. Half the African continent, inverted as a floor, in the absolute dark, under 100 to 180 kilometers of water, under 150 to 200 kilometers of ice. Hydrothermally active, chemically complex, warm enough for liquid water, present for 4 billion years. The biological productivity per unit area at deep ocean hydrothermal vents on Earth is low compared to sunlit surface ocean environments. The energy flux is orders of magnitude smaller. So the biomass density per square kilometer of Pluto's ocean floor would, if life exists there at all, be tiny compared to the biomass density in Earth's productive ocean regions. But tiny biomass density across 16.6 million square kilometers of surface area, over 4 billion years of continuous operation, accumulates into something. The total biomass of Earth's deep biosphere, the microbes living in rock and sediment kilometers below the surface, deriving energy from water rock chemistry and not sunlight, is estimated at between 15 and 23 billion tons of carbon. This is comparable to the total biomass of all life on Earth's surface. The deep biosphere is invisible, inaccessible, ignored for most of the history of biology, but it is enormous. If Pluto's ocean contains life at even a small fraction of the productivity of Earth's deep biosphere, the total biomass in that ocean accumulated over 4 billion years would not be trivial. This is not a prediction. This is a scaling argument. It shows what the numbers imply if the conditions are right. And the conditions, based on everything we know, may very well be right. Part 13. The mission we haven't built. In the institutional language of planetary science, the highest priority missions are called flagship missions. These are the large, expensive, transformative missions Cassini, Curiosity, Voyager, new horizons that represent the full ambition of what space science can accomplish. They cost between $2 and $5 billion. They take 10 to 15 years to develop and build. They achieve science that smaller missions cannot. Multiple groups have studied the concept of a Pluto orbiter mission. The studies are detailed, they are serious. The science case is, by any objective measure, compelling. The engineering challenges are substantial but not insurmountable. A Pluto orbiter would require a nuclear power source, specifically a multi-mission radioisotope thermoelectric generator, the same technology used on New Horizons and Curiosity. Solar power is not viable at Pluto's distance. This technology exists, has been used on multiple missions, and continues to be developed by the Department of Energy in partnership with NASA. A Pluto orbiter would require a travel time of approximately 10 to 15 years using current chemical propulsion technologies, with a Jupiter gravity assist to maximize speed. This is the same approach used by New Horizons, which traversed the same distance in 9.5 years. Future propulsion concepts, nuclear thermal propulsion, nuclear electric propulsion, could potentially reduce transit time significantly, but the mission can be accomplished with existing technologies. Once in orbit, the spacecraft would spend multiple Plutonian years, no, not 248 Earth years each, but rather in low orbits that allow detailed surface mapping, systematically imaging and analysing Pluto and its moons, sounding the ice shell with ice-penetrating radar to directly image the ocean below, measuring the heat flux from the interior, analysing the atmospheric chemistry with high-resolution mass spectrometry, and characterising the surface in enough detail to identify the most promising landing sites for a future surface mission. The ice-penetrating radar capability is not exotic. The same technology is being flown on the Europa Clipper mission, which launched in October 2024 and is currently en route to Jupiter's moon Europa. The instrument can see through kilometers of ice and map the structure of what lies beneath. Applied to Pluto, it would directly image the ocean, confirming its existence, measuring its depth, characterizing the ice-ocean interface, identifying locations where the ice is thinnest and where connection between the ocean and the surface might be most likely. A Pluto lander is a more distant prospect, requiring advances in autonomous navigation and extreme cold operation, but lander technologies are being developed. Europa lander concepts exist. The problems are being worked on. The science is ready. The technology roadmap exists. The funding has not been allocated. In the most recent Planetary Science Decadal Survey, the 10-year strategic planning document released in 2022 that sets NASA's priorities for the following decade, Pluto was not selected as a top priority flagship mission. The survey recommended prioritizing a Uranus orbiter and probe as the highest priority flagship mission, followed by Enceladus missions. Pluto received acknowledgement as a high priority target for a future decade. The scientists who study Pluto understand the process. They are working within it, writing papers, presenting at conferences, building the evidence base, making the case in the language of institutional science, methodically, carefully, with appropriate hedging and precise language and peer-reviewed quantitative arguments. Outside the institutions, the case is less hedged. There may be life beneath the ice of Pluto. The conditions are right, the chemistry is right, the time is right, the energy is right. We do not know because we have not gone back. And we have not gone back because we have not decided to. Part 14. 4 scenarios at the end of time. When the mission eventually flies and the scientific community is increasingly confident that it will, that the question of prioritization is one of decades, not generations, what will it find? Let's go through the 4 scenarios carefully, not because we can predict which one is true, but because thinking through the scenarios is itself a form of understanding. Each outcome changes things. Scenario 1. The ocean is frozen, or mostly frozen. The geological activity we observe on Pluto's surface is interpreted as evidence of current subsurface liquid water. But interpretation involves assumptions, and assumptions can be wrong. It is possible that a more conservative model is correct, that the ocean partially refroze millions of years ago, that the geological activity we see is the residual expression of a cooling interior rather than an active liquid one, that the mass anomalies and the fracture patterns record the history of an ocean that no longer exists in liquid form. This scenario would be disappointing but scientifically important. It would tell us the duration threshold for ocean world activity at Pluto-like distances from the Sunday. It would help constrain models of tidal heating and radiogenic decay in small icy bodies. It would narrow the population of ocean worlds in the outer solar system. And it would not completely close the question of life. Even a refrozen ocean could preserve biological material, frozen, dormant, chemically preserved in the ice. Extremophile microbes on Earth can survive in ice for hundreds of thousands of years. 4 billion years is far beyond that threshold, and ice preservation over that timescale is not chemically plausible. But the frozen remnants of a formerly liquid ocean would not be entirely without interest from an astrobiological perspective. Scenario 2. The ocean is liquid but chemically barren. The ocean exists. The geological evidence was correct. The chemistry is there. Water, dissolved minerals, hydrogen from serpentinization, organic molecules delivered from the surface. But life did not arise. The specific sequence of events required for a biogenesis, the emergence of self-replicating chemistry from non-living precursors, did not occur. This scenario would be the most scientifically nuanced. It would tell us that the conditions for life are not sufficient for the origin of life, that there is some additional factor, some specific condition or threshold that was present in Earth's early ocean and is absent from Pluto's. Identifying that missing factor would be one of the most important contributions to origin of life research in decades. The null result is a data point. The absence tells us something about the gap between chemistry and biology. Scenario 3. Microbial life exists at the ocean floor. Methanogens or their Plutonian equivalents. Single-celled organisms consuming hydrogen and exhaling methane, living at the rock-water interface, perpetuating themselves through the slow chemical cycles of the deep ocean. Biochemically different from Earth life with a different genetic encoding system, different membrane chemistry, different amino acid repertoire, representing a completely independent origin of life, but recognizably alive in all the ways that matter, metabolizing, reproducing, evolving. The discovery would be civilizational in its impact, not just because life exists beyond Earth, but because a second origin of life in our own solar system means life is not an accident. It means life is what chemistry does, given liquid water and chemical energy and time. It means the probability of life in the universe is not 1 in a trillion, but something far, far higher. Every subsurface ocean, in every solar system, around every one of the 400 billion stars in our galaxy and the 2 trillion galaxies in the observable universe, is a candidate biosphere. The universe would not be a lonely place. It would be a populated one, almost inconceivably populated. And we would have learned this not from a radio signal from a distant civilization, not from a dramatic first contact, not from anything we saw coming. We would have learned it from a microbe living in the dark beneath the ice of a world we once decided was too small and too cold and too far away to matter. Scenario 4. Something more complex. This scenario is not supported by the current energy budget models. The productivity of a chemically driven deep ocean is low. Complex multicellular life requires far more energy than is likely available in Pluto's ocean. But the universe is large and the history of science is long, and the lesson of that history is that the things we say are impossible have a tendency to be found in the places we finally decide to look, quietly existing. Pluto's ocean has had 4 billion years. 4 billion years is a very long time for the improbable to become possible. We do not know, and that is exactly the point. Part 15. The Fermi Paradox Resolved in Ice. Enrico Fermi asked his famous question at a lunch table in Los Alamos in 1950. If intelligent life is common in the universe, where is everybody? If there are civilizations out there, why haven't they contacted us? Why haven't they visited? The universe is billions of years old. There has been plenty of time. Where is the evidence? The Fermi paradox has generated an enormous literature of proposed resolutions, from the sobering to the terrifying to the deeply unsettling. Perhaps intelligent civilizations inevitably destroy themselves before achieving interstellar capacity. Perhaps the distances are simply too vast. Perhaps the universe is stranger than we understand, and the silence means something we haven't yet grasped. Pluto offers a different kind of resolution, a quieter one. If life in the universe is primarily microbial, if the vast majority of inhabited worlds are ocean worlds with sealed subsurface oceans, too deep to receive sunlight, too cold to develop surface chemistry, hosting life that is simple, resourceful, and entirely without the capacity or the interest in interstellar communication, then the universe can be full of life and completely silent simultaneously. The silence does not mean the universe is empty. It means the universe's life is mostly in the dark, mostly under ice, mostly eating hydrogen and exhaling methane and cycling through its patient evolutionary loops, entirely unaware that somewhere in the inner solar system, a pale blue dot has been pointing its radio telescopes outward and listening for a reply. Most life in the universe, if Pluto's ocean is any indication, will never build a radio telescope. Most life in the universe will never develop hands or eyes or nervous systems complex enough to ask questions. Most life in the universe will be doing what Pluto's microbes, if they exist, are doing: surviving, metabolizing, reproducing, evolving, slowly, in the cold and the dark, without history or language or curiosity or art. This is not a bleak resolution. It is a humbling one. It suggests that complexity, the kind of complexity that builds civilizations and asks questions, is rare in the universe even if life is common. That intelligence is an unlikely further step beyond the already unlikely step of life. That we may be profoundly unusual not for being alive, but for being aware. And if that is true, if microbial life is common and intelligence is rare, then the Fermi paradox is not a paradox at all. It is the expected result of a universe in which life is everywhere and self-awareness is nearly nowhere. We would not hear from the universe's life because it cannot speak. It can only persist. Part 16. The long silence and the decision. Pluto will still be there. Not a comforting thought in the way that most reassurances are comforting. It does not make the wait feel shorter or the cost feel smaller, but factually, operationally, it is the truth. Pluto's orbit is stable. Its ocean is not going anywhere. The hydrogen at the ocean floor will still be available. The chemistry will still be running. The 4 billion year experiment will still be in progress. The universe does not notice whether we look. Only we do. And right now, we are not looking. We flew past once. We took photographs. We wrote papers. We updated our models. We argued at conferences and in peer-reviewed journals about what the data implies. And we moved on to the next mission, the next budget cycle, the next competition for limited resources among many compelling targets. And every year that passes without a Pluto orbiter mission is a year of questions that remain unanswered. Not permanently, the questions will still be there when we finally decide to go. But it is a year in which, somewhere in the scientific community, a student who might have devoted their career to Pluto science chooses a different path. A year in which a technology that would be useful for the mission does not receive the development funding that would advance it. A year in which the institutional momentum toward a Pluto orbiter fails to build. The scientific community understands this. The argument for urgency is not that Pluto is going anywhere, it is that we are. Every generation has its scientific questions. Every era of science has its great unknowns. The question of whether life exists beyond Earth is this era's defining question, the one that, if answered, changes everything. And one of the most accessible, most scientifically compelling, most technically feasible pathways to an answer is sitting 4 billion kilometers away, under 150 kilometers of ice, in an ocean that has been patiently waiting for 4 billion years. The decision is not technical. The technology exists. The decision is not scientific. The science is compelling. The decision is about what we value, about what we spend our civilization's resources on, about whether the question of whether we are alone in the universe is important enough, urgent enough, worthy enough to justify the sustained investment of time and money and talent and ambition required to go find the answer. Part 16a. The generation that decides. We are not the last generation that will look at the solar system and not know whether it contains life beyond Earth, but we could be, if we choose to be. The children who are in school right now, the 7-year-olds learning the planets in order, the 12-year-olds building cardboard model solar systems for science fairs, the 17-year-olds deciding whether to pursue astronomy or engineering or chemistry, these are the people who will receive the results of a Pluto orbiter mission. If that mission is launched in the next 15 years, these are the people who will sit in front of a screen, somewhere in the 2050s, and watch the first radar image of Pluto's ocean materialize line by line as the data arrives from the outer solar system at the speed of light. These are the people who will see the first isotopic analysis of Pluto's atmospheric methane and know for the first time whether the carbon ratio points toward geology or toward biology. These are the people who could know the answer, but only if we decide today that the answer is worth finding. The history of space exploration is a history of choices made by one generation on behalf of the next. The decision to launch Voyager was made by scientists and engineers in the 1970s whose work provided the foundation for everything we now know about the outer solar system. The decision to build Cassini was made in the 1980s by people who knew they would be retiring before the spacecraft reached Saturn. The decision to fund New Horizons was made against intense opposition by a community that believed future scientists would thank them and was right. Every generation of planetary scientists has made decisions whose full consequences they would not live to see. The decision about Pluto belongs to us. The question is not whether the science justifies the mission. It does. The question is not whether the technology exists. It does. The question is whether we have the institutional courage and the civilizational ambition to commit, right now, to answering the most important question in the history of our species. Are we alone? The answer may be 4 billion kilometers away, in an ocean under ice, 4 billion years old, waiting in the dark. We have the spacecraft designs. We have the instruments. We have the trajectory analyses. We have the science case. We have the engineers and the scientists and the mission architects who could build this mission. We are missing only the decision. And the decision, unlike the mission itself, unlike the ocean, unlike the 4 billion years of patient chemistry waiting at the floor of Pluto's dark sea, cannot wait. Part 16b, What the Darkness Teaches. There is a final thought that this story demands. Not a scientific one, not an engineering one, not even an astrobiological one, a human one. We have spent this entire documentary looking outward, at Pluto, at the ice, at the ocean, at the chemistry, at the possibility of life in the dark. But the darkness at Pluto teaches something that is fundamentally about us, about the human tendency to decide in advance what is worth seeing, about the cost of assumptions so deep and so unexamined that we cannot recognize them as assumptions at all. We decided Pluto was dead without looking carefully. We decided it was not worth the investment. We decided that a small, cold, distant world could not possibly repay the cost of a serious mission. We decided these things not maliciously, not negligently, but with the confident, reasonable, institutionally supported logic of people who thought they already understood the situation. We were wrong. The universe is indifferent to our assumptions. It does not shape itself around our predictions. It does not produce interesting phenomena only in the places we think to look. It produces extraordinary things everywhere in the cold, in the dark, at the edges of what we have decided matters. And it waits, with a patience measured in billions of years, for us to get around to looking properly. Pluto waited 75 years for a spacecraft. Its ocean waited 4 billion years to be discovered. The lesson is not just that we should go back to Pluto. The lesson is that every time we decide, without careful examination, that something is not worth looking at, every time we apply the intellectual shortcut of probably boring to anything in the universe, we risk missing exactly the thing that changes everything. The universe does not mark its important discoveries with bright signs. It marks them with darkness, with distance, with apparent smallness, with a superficial appearance of irrelevance. Pluto looked like a runt, a mistake, a dwarf planet at the bottom of the solar system's hierarchy. It has an ocean. It may have life. And it has been there, silent, patient, indifferent to our dismissal, holding its secrets under 200 kilometers of ice, waiting for the day when we finally decided it was worth looking at properly. That day came once, briefly. In 2015, a piano-sized spacecraft screamed past at 50,000 kilometers per hour and took photographs that broke every model we had. The day needs to come again. This time, it needs to stay. There is a version of this story where we go to Pluto, we build the orbiter, we penetrate the ice with radar, we map the ocean floor, we measure the chemistry of the water and the atmosphere with perfect precision, and we find nothing. No isotopic biosignature in the methane, No anomalous organic chemistry patterns that suggest biological processing. No evidence of biological material in the ice. Nothing alive. Nothing that was ever alive. Just water and rock and hydrogen and chemistry, running patiently, generating energy, sitting in the dark. This outcome has its own importance. It would mean that 4 billion years of liquid water in contact with a hydrothermally active rocky core, with organic chemistry delivered from the surface over billions of years, with all the ingredients and all the time and all the energy, this was not sufficient for life to emerge. Which would mean that life on Earth is either extraordinarily unlikely a chance event of almost incomprehensible improbability that happened once in the solar system and perhaps rarely in the universe, or that the conditions here, the specific conditions that life required to emerge, are more restrictive than we currently think. That there is some additional factor, some specific ingredient, or specific process or specific set of circumstances that was present on early Earth and was not present in Pluto's ocean. Identifying that missing factor, the difference between the place where life did emerge and the place where it did not, would be one of the most important contributions to origin of life research in the history of science. The null result does not close the question of life in the universe. It narrows it, it sharpens it, it tells us where to look more carefully, what conditions to prioritize, what factors matter most. Science wins in every scenario. The universe reveals something important regardless of what Pluto's ocean contains. The only way science loses is if we never go. Part 18. The pale blue dot at the edge of everything. On the 14th of February 1990, the Voyager 1 spacecraft, having completed its primary mission of exploring the outer solar system and now sailing in the direction of interstellar space, was commanded to turn its camera back toward the inner solar system and take a portrait. The resulting image showed the Sun and several of the planets as tiny points of light in the darkness. Earth appeared as a barely visible dot, a fraction of a pixel suspended in a shaft of scattered sunlight. Carl Sagan, who had campaigned for the image to be taken, wrote about it in 1994. He wrote about what it meant, about the smallness it revealed, about the isolation, about the single frame that contains every human who ever lived, every joy and suffering and achievement and failure, every empire and civilization, every war and every peace. The pale blue dot. In 2015, when New Horizons was preparing for its Pluto flyby, the spacecraft briefly turned its own camera back toward the inner solar system. Earth was visible as a small, bright point of light. From Pluto's distance, approximately 4.8 billion kilometers at the time, the Sun appeared only 1/1000th as bright as it does from Earth. The solar system's center was a bright star surrounded by darkness. Earth was one of the faint points around it. From Pluto, Earth is not a pale blue dot. From Pluto, Earth is invisible to the naked eye. This is the perspective that the outer solar system gives us. This is what Pluto sees or would see if it had eyes. If anything in its dark ocean had evolved the biology of sight over 4 billion years of evolution, in complete darkness, where eyes serve no purpose. Nothing on Pluto knows we exist. Nothing in Pluto's ocean has ever detected a photon of light from Earth, because the light from Earth, at that distance, is negligible. Nothing in that ocean has felt our gravitational influence, because at that distance, our mass is insignificant. We have sent one spacecraft once, which flew past at 50,000 kilometers per hour and spent a few hours in the vicinity before continuing outward into interstellar space. And from that single brief encounter, from that one pass, that one set of instruments, that one trajectory, we inferred a global ocean. We identified the chemistry of life's precursors. We found young mountains and active geology, and an atmosphere and complexity that shattered every assumption we had made about what a world at that distance could be. What would a second encounter find? What would an orbiter, circling for months or years, mapping every kilometre of the surface, sounding the ice with radar, analysing the atmosphere with precision instruments, find? We do not know, but the history of planetary exploration says the answer would astonish us. Every body we have visited in detail has astonished us. Every one. Mercury has a magnetic field and volcanic plains that should not exist. Venus has an active geological surface beneath its acid clouds. Mars has ancient river valleys and a magnetic field memory and organic molecules in its soil. The Moon has ice in its permanently shadowed craters. Io has 100 active volcanoes. Europa gleams with an ice shell that may crack and flex and connect its ocean to space. Enceladus blasts its ocean directly into the void. Titan has rivers and lakes of liquid methane and a chemistry more complex than any other body in the solar system except Earth. Every body astonished us. Pluto astonished us. And we have only seen one page. Epilogue. The world that waited. There is a small, bright point of light at the edge of the solar system. You cannot see it with the naked eye. You need a telescope. Even through a modest amateur telescope, it appears only as a point, not a disk, not a surface, not a world. Just a point of reflected light, drifting slowly against the background stars, completing one orbit of the Sun every 248 years. That point of light contains mountains. It contains plains of nitrogen ice that glow in the dark and convect and reshape themselves over geological time. It contains an atmosphere so thin and blue it is barely distinguishable from the darkness. It contains a companion moon half its size, locked in a gravitational embrace so intimate that the two bodies orbit each other around a point in the empty space between them. And beneath the ice, beneath the frozen nitrogen and the methane blades, and the water ice and the geological history of 4.5 billion years of cold chemistry, there is an ocean. An ocean older than life on Earth. An ocean deeper than the deepest trench in our own seas. An ocean powered by the slow, patient chemistry of rock and water, sustained by the gravitational embrace of a moon, sealed from the universe by a roof of ice 200 kilometers thick. An ocean that may be empty. An ocean that may be alive. We built a spacecraft the size of a baby grand piano. We aimed it at a point in space 9 years in the future. We flew past at 50,000 kilometers per hour and spent 4 hours photographing a world we had never seen. We received the images over weeks, trickle by trickle, at data rates that would embarrass a 1990s modem, and what those images contained ended permanently, the idea that Pluto was dead. It is not dead. The question, the real question, the one that matters, the one that changes everything if the answer is yes, is still unanswered. The ocean has been there for 4 billion years. It has kept its secrets with extraordinary patience. It has given us clues, the anomalous mass distribution, the young surfaces, the active geology, the extensional fractures, the methane in the atmosphere. It has told us, in the language of physics and chemistry, that it is there, that it is liquid, that it is warm enough and old enough and chemically rich enough for the question to be worth asking. Now we have to decide whether we are brave enough to ask it properly. Not with a flyby, not with a photograph, with a mission that stays, that orbits, that measures, that listens, that sends its instruments into the ice and its radio signals back to Earth across 5 hours of space and waits, with whatever patience machines can embody, for the ocean to tell us what it contains. The universe does not give answers for free. It gives clues. It gives data points. It gives anomalies and fractures and isotopic signatures and atmospheric hazes and young mountains where old ones should be. And then it waits, as patient as an ocean under ice, for something curious enough to ask the follow-up question. We are curious enough. The only question now is whether we are willing enough. Pluto is not going anywhere. Neither is its ocean. Neither for a little while longer are we. Go find out what is down there. The smallest worlds carry the deepest secrets. The coldest places hold the warmest possibilities. And the thing we demoted, dismissed, and forgot about may be the thing that answers the oldest question we have ever asked.